Hi, my name is Andrew Hood, and this is Lab 3, the magnetic field of permanent dipole magnets. So to start off, we have the Biot-Savart law, which relates the strength, direction, and magnitude of an electric field with its persistent current. It can be applied to magnetism by substituting the persistent current with persistent magnetism, such as through a field created by a permanent dipole magnet. Additionally, for this experiment, it's important to note that cell phones have magnetometers built in that can be used to detect field strength and direction, and that we can determine the magnetic dipole moment of a magnet based on the strength of the measurement at a distance, through the Biot-Savart law. Some assumptions and methods. Basically, an apparatus was constructed using a non-conductive ruled measuring device, such as a yardstick, and a magnetically oriented smartphone, as shown below. The measurement apparatus will align so as to negate the magnetic effect of the Earth on the experiment, and the strength of the magnetic field along isolated axes can vary at varying distances, can be calculated, and will give a constant exponential factor according to the Biot-Savart law. So some results. Basically, the exponential factor we found from our experiment is 2.56. We were able to use the measurement data from the apparatus to construct a regression as shown later on. And the dipole moment of the magnet was found to be 3.13 amps meters squared. Now, the measured distance, or the measured d vector we found is shown here, as well as the calculated d vector. So some calculation computation. Basically, we constructed an Excel spreadsheet with data shown here and use that data to construct a regression using basically this equation: the natural log of b equals the natural log of k plus n times the natural log of r. R20, R70, etc. That corresponds to the distance where the b value is 20 microteslas or 70 microteslas, etc. So in this case, the natural log of k, it can be translated from the y-intercept, and it gives a value for k that we can use in this equation, which is basically the b value equals k times r to the n. N in this case is the slope of the regression, which was 2.5 or negative 2.56. We can combine this with the Biot-Savart law for magnetism and derive the magnetic dipole strength of the magnet. Additionally, we took this information and constructed a Python code that would give us the, straight calculation using that the Biot-Savart law for our data here. Parts of the code are shown here, as well as the total output of the code. The orange vectors are the magnetic field direction there, and the magenta arrow is the perpendicular field force. Other parts of the code shown here construct different parts of the code that aren't really related to the calculation. Things like, vector components and the little picture of the magnet itself. In conclusion, the calculated d vector differs from the measured d vector. The x component's off by, a factor of about 100% in error, and the y component is about an order of magnitude off. The measured B net is close to reported for the value in Atlanta. We measured it to be about 49.5 microteslas versus the 49 microteslas that we were given as the value there. The N value is significantly different than 3. That's the minus 2.56. It is supposed to be 3, and that leads to about a 14.5% error. So some of the error in this experiment can be derived from some of our methodology. All of the measurements taken use a three-dimensional field and strongly interact with things in their environment. The calculations for the Python flow script we use only uses 2 dimensions, basically. Again, magnetic interference from buildings, the cell phone battery, virtually any metal in the area could throw these results off. Additionally, just measurement error itself could be, a source of some of these errors. For this lab, I used pictures from the experimental guidelines given to us by the course instructors, and I created the code using GlowScript 3 as shown here. Thank you and have a good day.